So let's work some problems that deal with orthogonal subspaces. Our first problem is problem 1C from the book. You will be asked to do problems A and B from problem 1 in your homework, so this is a good one to pay attention to. Well, this and the next one will both be very related to the problems you'll be working on in your homework. We are given a matrix A, and we're going to find bases for 4 different subspaces. This is very similar to the stuff that we did back in section 3.6, but since we've been talking about row, column, and null spaces a lot in this section, it's a good idea to remember how exactly that works. So let's start off with A itself. Well, we have our A, and what are we going to do to try to find a good basis for the row space? Well, all we need to do is reduce this to, well, reduce row echelon form. That's probably the best thing to do here. So I'm going to go ahead and first move this second row to my first row to make use of that 1. And then I'm going to try to convert all the rest of them to zeros. So this 2, I'm going to take 4 times this 3 and subtract it. I'm going to get a negative 14. I'm going to have this 1 minus 2 times 3 will give us a negative 5. And finally, this 4 minus 3 times 3 will give us another negative 5. Of course, we don't want to have all these in here. We'll go ahead and divide this second row by negative 14. I mean, that seems like a fun thing to divide by, but we're just dividing negative 14 by itself, so we get a 1 here. And then we're going to use that 1 to not only cancel out the stuff down here, which is really easy because we can just add 5 times it to both of those, but we'll also use it to cancel out that 3. We can just subtract 3 times that 1. And we get this thing. So, ignoring these bottom 2 rows, we can see that a good basis for our row space is 1, 0 and 0, 1. So you could say R of a transpose is the span of the 2 vectors 1, 0 and 0, 1. Very nice basis. One thing to note here is it's 2-dimensional, but we also do know, because it's actually a subspace of R2, that it couldn't be anything more than that anyways. 2-dimensional is the biggest it could be. The only thing we really found out here is that it's not 1-dimensional. In fact, the row space of A is actually all of R2, which is very nice because that also means that the null space of A, well, it's actually empty. I mean, the null space has a 0 vector in it, of course, but there are no other vectors in it, because the orthogonal complement of all of R2 is just the 0 vector. It's one thing. And if you want to say what a basis for this is, you could actually say it's the empty set. You can't have any basis vectors. That's why we say that the space with just a 0 vector in it has dimension 0, because they're literally a basis for it consists of 0 vectors. I mean, essentially, even if you just take 0, the vector 0 by itself, it's not linear independent at all, because we can multiply by something and get the 0 vector even if we multiply by something non-zero. So it's a little bit tricky to think about that, but especially when they're specifically asking for a basis here, but that's what we have. So null space is empty, or has an empty basis. I mean, we could also have made a column of all zeros over here and tried to solve, and seen that the only possibilities is the 0 vector. Now, what about the column space? Now, we did see before that we can find a basis for the column space by just looking at where the leading ones are. The fact that we have leading ones in our first and second column, the only two columns, that means we could take both of those two columns to be a basis for the column space. In fact, it is a basis. But we're going to go ahead and look at its transpose and do the same thing with the transpose. This will allow us to get a simpler basis for the column space, and it'll also allow us to find a basis for this other space, the null space of A transpose, which is actually a lot trickier to get than if we didn't start with the A transpose and actually try to put into row echelon form. So, what is A transpose? Well, we take our first column as our first row, take our second column as our second row. We'll go ahead and reduce this. I'm going to start by adding. Well, we should probably actually multiply our second row by 2 first. That'll probably make it a little easier to work with. And then if we add our first row to our second row, that will go ahead and cancel out that -4 to give us a 0. It'll leave this first row alone. And unfortunately, we get some pretty big numbers here. So we have, what, 7, 4, and 11. If we wanted to do anything more with this, we'd probably end up either making our numbers a lot bigger or having to deal with fractions. So maybe we'll go ahead and leave it like this. We can say that our column space is a span of 2 vectors, 4, 1, 2, 3, and 0, 7, 4, 11. And this allows us to go ahead and then also figure out what the null space is going to be, the null space of the transpose at least. Basically, if we augment this with a column of zeros, and try to solve these two equations, we can go ahead and figure that out. Now, keep in mind here, we actually do have 2 free variables, x3 and x4, if we assume that we're dealing with x1 through x4 as variables. So we can go ahead and pick numbers for those and actually get vectors using that. I'm going to go ahead and pick specifically a case where x3 is equal to, let's do 14, and x4 is equal to 0. I'm picking 14 here because I know that will allow me to get integers out rather than having to deal with too many fractions. Because then what do we have? We have 7 times x2 plus 4 times x3 plus 11 times x4 is equal to 0. If I plug those in and I solve for it, we have 7x2 plus 4 times 14, and then the 11x4 goes away. That's going to give me x2 equal to -8. I'm going to have to move this to another page. And then going for x1, we have 4x1 plus x2 plus 2x3 plus 3x4 is equal to 0. So our first row is 4, 1, 2, 3. If we use our results then, we have x1 is equal, well, we don't know what x1 is. That's what we're trying to find. We have x2 is -8, x3 is 14, x4 is 0. So ultimately here we get that x1 is equal to -5. So here we get the vector -5, -8, 14, 0. It's probably as simple as we can make it without dealing with any fractions, because these don't have any common factors. Then we need another vector. Basically, these are all the vectors where the last coordinate is equal to 0. But what if we want to pick x4 to not be 0? Let's pick it to be 14 as well. But in this case, we're going to let x3 be 0. Then doing the same thing, using the same equations. Here we're going to let we're trying to find x2. We're letting x3 be 0, so this goes away. And now we have 11 times 14. If we solve that one, we get what? X2 is negative 22. And we do the same thing over here, using the same equation. Again, x2 is negative 22, x3 is 0, so that goes away, and then x4 is 14, and ultimately we actually get negative 5 again. That's kind of interesting. So we get a vector of negative 5, negative 22, 0, and 14. So you could say, in this case, that the null space of A transpose is equal to the span of these two vectors. And there we go. Now we can actually test to make sure this worked out, make sure we didn't do anything wrong, by showing that these vectors in the null space of A transpose are in fact orthogonal to our vectors in our column space. So we can test to see if the scalar product of each of these two vectors is with these two vectors down here, if those always come out to be 0. And if they don't, then we did something wrong. But I'm going to assume that nothing went too wrong here, and let's just move on. But this is the way you would approach these problems. Just kind of didn't turn out maybe as nice of an answer as we might have wanted to get. But it's something that we can do. Now in problem 3, we're going to try to take a subspace of R3. We're not going to start with a matrix, but we're going to take a subspace, and to find the orthogonal complement of that subspace, we are going to introduce a matrix. Matrices turn out to be very handy for us in this context as well. Big surprise. We've been using them all the time, and we're just going to keep using them. But we're going to say that we have a subspace of R3 spanned by two vectors. X is x1 through x3, y is y1 through y3, and we're going to combine those into a matrix, where each of those becomes the rows of A. The first row of A is x, or technically x transpose, and the second row is y transpose. This means that, well, the row space, or as we'd like to say, the R of A transpose is in fact S. That's kind of the whole point. And that means that the null space of A, which remember we have is the orthogonal complement of the row space, is then the orthogonal complement of S. That's actually all we need to do for A. Just use the fact that we know that the row space of A is S, and the null space is the orthogonal complement of that. So what about B? In B, we're actually going to pick some numbers. We have two specific vectors, 1, 2, 1, and 1, negative 1, 2. We are going to find the orthogonal complement of the subspace of R3 spanned by those two particular vectors. So again, we're going to turn this into a matrix. First row is going to be 1, 2, 1. Second row is 1, negative 1, 2. How do we work with this? Well, we know its row space is this subspace that we're working with. We want to know the null space. So how do we find the null space of this matrix? We do Gaussian elimination again. So if we subtract the first row from the second row, so we get our second row now becomes 0, negative 3, 1. Again, I don't want to get into too many fractions, so I'm not going to divide this row by negative 3, but we can already see that x3 is going to be a free variable. So we can go ahead and pick something for x3. Again, I'm going to pick 3 here just so I can avoid fractions. That allows us to say that negative 3x2 plus 3, because that's what x3 is equal to 0. So x2 is going to be 1. And then from our first row, x1 plus 2 times x2, which is 1, plus 1 times x3, which is 3, is equal to 0. So x1 is going to be another negative 5. But based off this one choice of x3, we are able to find out what the vector was. And in fact, picking any other value for x3 is just going to give us another, it's going to give it scale all of this by the same factor. So we can see here the null space of A, or in fact, you could say the orthogonal complement of S, where S is the subspace spanned by 1, 2, 1 and 1, negative 1, 2, is in fact the space spanned by the single vector. Sorry, we need to start with the negative 5, 1, 3. Okay. Now, okay, yeah, let's leave it with that. So we're spanned by that one single vector. In your homework, you get to do this process as well in problem 4. So it's essentially just the same thing. And this process does generalize. Here in part A, we did specify that we were specifically working in R3, and we had 2 vectors. If we have Rn and we have, say, R vectors, we would still do the same thing. We would put those vectors as our rows, and then use the fact that we know the null space of that particular matrix is going to be the orthogonal complement of our row space to actually find the orthogonal complement of the space that the subspace that we're working with. The process is exactly the same. This just happened to be working with 3 and 2 as our dimensions. Now, this chapter doesn't really, the section, I guess I should say, the section doesn't have a lot of problems with numbers in them. Most of them are already going to be in your homework, or we've already gone over. The rest are actually proofs. So I'm going to work through one of those that I find kind of interesting, and we'll leave it at that. I'm not assigning you any proofs in this section. The assignment for this week will be long enough as it is. Mostly because of the next section. 5.3 is kind of an intense section. So we'll get to that. Alright, so here we're starting with an m by n matrix that we say it has rank R. We're going to pick some basis for the row space. That's what R of A transpose is. And then this is saying that we can find a basis for the column space by just multiplying each of our vectors by A. Now that seems a little too easy, but can we make it work? So how do we figure out if this is a basis? Well, we have to show that it's linear independent, and we'd have to show that it spans the column space. But we actually get something for free here. Remember, we know that the dimension of the row space and the dimension of the column space, these are always equal for any matrix. I don't know if we named it, but we talked about why we don't need a separate name for the row rank and the column rank. We just have rank because it's the same dimension in both cases. So because we have the same dimension, we actually only have to show one. We only have to show either that they're linear independent or that they span the column space. We don't have to show both of them. Let's just show that these are independent, and we'll be done. So we'll assume we have some coefficients, C1 through CR. These are real numbers. Such that our linear combination of the AXI's equals 0. What can we do with that? If we can show that all the c's have to be 0 because of that, then we'd be done. Well, let's factor out a. We can actually move the c's past the a because they're just numbers. So we can pull the c's over to the x's, and then we can factor out a from everything. So a times c1 x1 all the way through cr xr. That's equal to 0. What does that mean? Well, that means that this vector here, the c1 x1 plus c2 x2 and so on through cr xr, this has to be in the null space of A. I mean, that's what it means. We have A times this vector is equal to 0. That's what it means to be in the null space. But we also do know that every single one of these x's is in the row space. It's, in fact, the x's are a basis for the row space. So this vector here, as a linear combination of things in the row space, it also has to be something in the row space. So it's in both of these. But remember, the null space and the row space are orthogonal complements of each other. And by one of the remarks on page 218, if we have two subspaces that are orthogonal to each other, their intersection can only have the 0 vector in it. Well, this vector that we have written out here is in the intersection because it's in both of them. That means that this vector has to be the 0 vector. There's no other choice. Well, remember, the x's are a basis. That means they're linear independent. If they're linear independent and we have a linear combination of them equals 0, that means that all those coefficients, they all have to be 0. All these c's have to be 0. And if all those c's are equal to 0, we just start with the assumption that this linear combination of the ax's is equal to 0 using those c's. And we got, eventually, that all the c's have to be 0. That means the ax's have to be linear independent. And so, like we said, we only have to show one of those two facts. We don't have to show they span. We already know now that they are a basis for the column space. So, once we have a basis for the row space, we can actually find a basis for the column space rather easily. Maybe that's another way that we might go about finding bases for the column space eventually. So for now, that's all we're going to do with it. So, all right. Again, we're going to get into using some of this stuff to solve a different type of problem next class in section 5.3. It's called the least squares problem. And we'll have lots of fun then. But for now, I'll leave you guys to that. So, see you.